This video by Andrej Karpathy is about creating a GPT model from scratch to generate text. In this case, in his example, he uses the corpus of Shakespeare writing and trains the model to create Shakespeare-like text. It's a great video. What I want to do in this video is to walk through the architecture without really looking at the code, but rather diagrams. So let's do that. So the first step, I'm going to talk about the data processing a little bit before we jump into the model. Say this is piece of the text from Shakespeare. You are all resolved rather to blah blah. What you need to do before you feed it into any model is to tokenize this. Tokenizing it is breaking it into chunks. And in the nanoGPT code, the token is just one character. So this is very trivial in this case. You pass it through tokenizer, it essentially becomes an array of characters, U, Y, O, U, space, A, R, blah, blah. And it turns out there are 65 unique characters. In other words, your vocabulary is 65. I will talk more about that. The next step is to encode it. What would feed into model is going to be number, and the output will also be numbers. So the first step is, once you have this array of characters, is to convert each of them into a number. And those numbers are actually arbitrary, as long as you keep it consistent. So the encoder here is just a dictionary that maps Y to a number, O to a number, so on and so forth. And here is the digitized representation of the text above. So Y is 37. By the way, capital Y is going to be a different digit than lowercase. But you say like letter A here and letter A, they should be the same number. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 39. It appears here, it appears here, right? So now you got the input formatted in a digitized or a number format. Let's talk about how the model would generate text. The next step here in the process. The way it would work is you give it some text, in this case the number representation of that text, say 37, the first one, and then pass it through the model. The model will always do the same thing, which is to predict the next token, or in this case the next character, given the history. So if it's 37, the next one probably, hopefully, will predict to be 53. And what it does next is that if you want to generate Shakespeare-like text, is to append that prediction to the end of the text that already exists. So you already had 37, you predicted 53, now you append to it, feed this to the model, 37 and 53, it will predict 59. And then you keep repeating this, attaching or appending the prediction to the last character in the text or string, and just keep going. This is called autoregressive modeling, where you make you use the predictions to create a history, essentially. All right. Now, when you look at the model architecture, you will see that you can't really feed into it an unlimited, boundless history of text to predict the next character. There is a constraint dictated by the architecture of that model. And that is what we call context window. Say the context window is 3. So if you had all that text, it takes the first 3, make a prediction, let's say 1. And then if you want to know what comes after 1, you have to shift the context window by 1, such that the context window remains 3. So now you will have 53, 59, 1, and then it will predict 3, and then you shift it again. So here we talked about tokenization, encoding, and this is the process of preparing the text. And we talked about how text is generated, which is an iterative autoregressive process. And we learned a little about context window. Even ChatGPT has a context window. They're huge, but they exist. And that is the amount of history that can be fed into the model. Right? Now, let's see what that looked like, or just reiterate, I guess. So you have a bunch of numbers, and the length of that array of numbers is your context size, in this case 3. You feed it into the model make a prediction of the next character. In other words, the model looks at that vocabulary size of 65 and the probability of each of those characters coming up next, then it finds the most likely character, or the character with the highest probability. Right. Now, the next step, or the next concept that you need to understand here is that when I showed this model to you, I wasn't 100% honest, because you can't really feed these numbers to the model. And the reason for that is the numbers are arbitrary. There's no reason why letter Y should be 37 and not 14. All we did here was just map them to a number so we can work with those numbers. In other words, 38 is not any closer to 37 than 52 is. Those distances don't mean anything. So what you want to do is this process of embedding, which is converting each character or each number that represents that character into a vector. So you got embedding is going to be essentially the first layer of your model. It takes that number, you feed it into this embedding thing, and it just gives you a vector. The vector here is like 0.12, and then this number, this number, this number. It's an array. And it has a size that you decide what it should be. And this is the second parameter you need to think about when you're building the model. So one was the context size, or the context window, how many characters in the history. And the second one is each of these characters, in what dimensionality do you want to represent it? What should be the size of that vector? That's the embed size. Right? All right. Now I'm going to walk you through the model. So far we talked about data preparation at the very top layer of the model. I'm going to zoom out a little bit so you know what's coming next. So this is going to be the architecture of the model, and then this is going to be the simplest one, and I will build on it to bring it to the final model that he and I actually used and made predictions. But I'm going to just zoom out a little more and see what I'm going to show you next. So I'm going to show you a simple one, kind of like a bare bone model. Then we're going to beef it up a little bit. Then we're going to beef that up a little bit. And we'll arrive at this final model. All right, so let's go back. The good news is if you understand this bare bone, that is essentially the main takeaway, the main message here. And by understanding this, you understand how transformers work, how attention mechanisms work. And that is important because right now all this breakthroughs and innovation in deep learning are with the use of transformer architecture. All right, so let's talk about this. So if you remember, I talked about context size, and then we just name it T, and T stands for time, and the embedding size, C, and C stands for channels. So you have the input, and the input was that text, an array of digits. The size of the array was the context size. And I'm showing letter T here to show that what comes out of this layer has the dimensionality of T. Now, you pass it through two embedding layers, actually. On top, I talked about token embeddings, which was take that number and convert it into an array of size C. But you need to do the same thing for the position of each characters. And I'm jumping ahead a little bit because right now, if you're not familiar with the transformer architecture, you wouldn't appreciate why you need to embed the position. So let me explain briefly why is it that you're going to embed or somehow take note of the positions of the characters. So as humans, we know the sequence of words or characters in a text really matter. It defines the meaning of it. So logically, you want to include that. And as humans, we start reading from the first letter to the last letter in a text. Transformers don't do it that way. They don't recursively, they don't sequentially go through the content. They look at it all at the same time. And you will see below that because the model doesn't go over each character in sequence and rather at the same time, you have to embed some notion of position into each character to not lose the meaning or the concept of position. Right? Now, the output of H is going to be a matrix of T by C. T because you have T number of characters in your context window, and C because for each of those characters now you have a vector of size C or embed size. And then you add them up together. And what you're doing here is that each of those characters is now represented by one vector, and that vector has meaning of the character itself, but also its position, right? And now you can look at each of those characters alone and have good amount of information about them, again, because the position of that character in the context window is embedded in that vector. And now what's going on next is the heart of the attention mechanism. And here's what happens. You're gonna use 3 linear layers, and I just call them query, key, and value, but they're essentially just a simple linear layer. You feed into it, a vector comes out of the, or matrix comes out of the same size, right? And then you do a scaled dot product, which is a matrix multiplication operation on those 3 vectors. Now let me explain what we're doing here, because that's really what this attention is about. What we're trying to say is that let's update each of these arrays or each of these embedding vectors that represent each character by the value of the characters that came before it. So if you're looking at the first character, there is really no characters before that, so that shouldn't change in that representation. But the second one could be updated by whatever value of the first character was. And for the third one, the first and the second are going to influence that. What is key here to understand is that in this communication layer, this is a communication layer. That's when all these characters in the context window have the opportunity to meet each other, find their affinity towards each other, and be influenced by each other. But that process doesn't have any trainable parameters in it. That is interesting. All the trainable parameters are in defining query, key, and value. Now, one final thing on this is that what you're doing here essentially is, for each of those characters, the query vector essentially says, this is what I'm looking for. And the key says, this is what I have to offer. And the value says, use this vector, this value, to update the embeddings. Right? So you feed it into this, and this linear layer is just an opportunity for the new embeddings to update their value. It is a computation layer. So this was the communication layer, this is a computation. That's the opportunity to adjust the values and for a model to train what to do with those embeddings. And what comes out of it is T by C size matrix. And by the way, that's the same size as here. So what you'll notice here is that the dimension of that matrix remains the same. What's happening here is that the values inside, which is the value, the embedding of each of those characters in the context window, are being updated. And by updated, I mean informed by the characters that came before it. Right? So finally, now you can just pass it through a linear layer and convert each embedding layer into, or each embedding vector essentially, into a vector of size of vocabulary or vocab size. If you remember, in our case, it's 65. And pass it through a softmax such that what comes out of it is the probabilities of each character coming after what you have right now. So that is a walkthrough of the bare minimum. This, what I've outlined by this dash line, is the head, what we call a head in the transformer architecture. And a head is an opportunity for each character or each token embedding to be updated and informed by the character that came before it. And these two last layers are just trained and then used to maximize the probability of the correct next character. All right? So that was a head, and what you could do next to beef it up is to have multi-head. So you have, in this case I have two. You have one head here, one head there. They do essentially the same thing, but with different parameter values. So these key, query key and value here are different from this. You have to train them separately. And the output vector size of these is half, and then you concatenate, bring them together. Now you will have essentially T by C. Now this is akin to convolutional neural network, where you're looking, instead of looking at different filters, you're looking at different key query and values. So this is multi-head. And finally, what you want to do is add another layer under this multi-head to, again, give it a chance to compute the optimal or the proper embedding values. And this whole thing, the multi-head plus that linear layer, and there's also like normalization and dropout, whatever, but that's not critical here, is what constitutes a block. Right? So we started with a head, and then with multiple heads together, we call it multi-head. And now the multi-head with a linear layer that comes after that constitute a block. Why is that important? Because now you can stack them up in this next illustration. So you have one block, two block, right? And let me see. The final comment I want to make here is that's actually, I think, the beauty of this transformer architecture is, other than the fact that it's not a recurrent mechanism, and it looks at all tokens at the same time. Another beauty of it is that it's very efficient. Let's look at an example of training data. Say this is the size of your context window. Say you are all, but it truncates here. And then that's like your training input, or Y. I'm sorry, X's. And then the Y, or the output that it should predict, is essentially all of this and the character that comes after that. And what that means is that, let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this already includes 10 training examples. And imagine if you have a batch of 100, that means at every pass of the model during your training, you actually are training the model on 1,000 data points. And it's really cool that you don't have to construct your training data into, in this case, into like 10 different data points, but rather just this. And all your training essentially in the block are a couple of just a couple of linear layers. Really, that's about it. Query key values, these are like a linear layers. You have a linear layer, and you have a linear layer that comes over here. And there's a normalization layer as well. All right. Now, with all that said, I'm going to show you the code very quickly. So these are the parameters of the model, if you like. And now you may have an appreciation for what we're talking about. The vocabulary size is 65. The embed size is 384. Each character is represented by a vector of size 384. And the context is 256. That means the number of characters that are fed into the model and the model has ability to read is 256. We're gonna, for our training, we're gonna iterate 5,000 times. We have a batch size of 64, which means at each pass of the model during training, you have 64 chunks. We were talking about multi-head. The number of head in each of those multi-head is 6, and the number of blocks is 6 as well. So we are stacking 6 blocks. In each of them, you have 6 heads essentially. And I'm using GPU to run this. Now, the data preparation is not the exciting part, but just letting you know that we have about 1 million characters in that Shakespeare text. And here's the model. So you have a class for head, class for multi-head. There's a feed forward, the linear layer. You define the block, which is a container for multi-head and feed forward and so on and so forth. Right. I ran the whole training from the start. So this sample output before training the model, something like this, completely gibberish. Then I trained the model, 5,000 iterations. As you can see, the training loss keep dropping, and here's my evaluation loss. And this is sample output from the model. I gave it a prompt or the start, something like this, bring me joy, blah, blah, blah. And then it generated the rest. And it actually looks pretty good, considering that it's predicting not the best next word, but the next character, the next letter. And we are not match, be bother, but find the fearer of him. As to the boy, the writ of his servant, blah, blah. So that's really cool. I hope that was useful.